Hello, everyone. My name is Shellen McCoy, and on behalf of the Atlantic Salmon Conservation Foundation, I'd like to say welcome to you today to our webinar. The series is made possible in thanks to the contribution of the Government of Canada. And for today's webinar, we have Kathryn Smith, and Kathryn is currently a PhD student under Dr. Barrett Kurlick in the Coastal Hydrology Lab at the Dalhousie University, investigating coastal thermal regimes and how their sensitivity to human alterations and climate change impact aquatic species. She earned her undergraduate degree in civil engineering at Dalhousie University, completing the cooperative program, and was a research associate for a few months prior to her graduate studies. She has received several scholarships to support her graduate research from the Dalhousie Aspire program, Nova Scotia Graduate Scholarship, Ocean Frontier Institute Opportunities Fund, Geological Society of America, and the Nova Scotia Salmon Association. Today, she's going to be discussing her initial findings of her research, which is on coastal river warming and cold water habitat loss to climate change. Just want to note that after the presentation this afternoon, we're going to be opening up the floor to question and answers. I'll remind the folks at the end of the presentation again, but when we do question and answers, it's going to be mostly during the chat where you can write in your questions and I'll read it out loud for Kathryn to be able to answer, or you can also put your hand up and I will unmute you and you will be able to ask your question yourselves. So for now, I will turn it over to Kathryn and looking forward to your presentation.
Thank you for the introduction and thanks for everyone attending the webinar today. So today I'm just going to talk a little bit about the preliminary work of my PhD research, focusing on coastal river warming, as well as looking at cold water habitat loss potentially due to climate change, and particularly focusing that with aquatic species like Atlantic salmon. So first, I'd just like to start off with acknowledging many contributions of various individuals for my research. So the first being my supervisor, Dr. Barrett Kurlick here at Dalhousie, as well as research support from my fellow colleagues at the Coastal Hydrology Lab. Spent countless hours in the field collecting data as well as bouncing ideas off of. And finally, I'd like to special shout out to Jason Karras-Allen, who actually successfully defended his master's research not too long ago, but on a study site of Basin Head Lagoon, which I've since taken on his initial data collection methods and have tacked that onto some of my research work as well. Then I'd also like to acknowledge and thank my funders, some of which are listed here, for the support of my graduate studies, as well as fieldwork that I conducted over the past 2 summers. So really, to outline today's webinar, I'm just going to provide a brief introduction to coastal rivers, as well as their importance of water temperature, specifically for aquatic species like Atlantic salmon. I'll then move into an introduction to estuary zones and how these areas play a critical role in the life cycle of Atlantic salmon. I'll then move into some of my specific research, so diving into my monitoring methods for my study sites, as well as giving a comparison of 4 of my study sites, so 2 of which are located in Nova Scotia, 2 of which located in Prince Edward Island. I'll then wrap it up and conclude with some final thoughts of my initial findings and really directing where this research will be heading for the later part of my PhD. So many on the call today, I'm sure are aware that many Atlantic salmon are adromatous species where the spawning adult, let's see if I can get my laser pointer. Here we go. So the spawning adult really lays their eggs in the river and freshwater systems, and once they hatch, they spend some time in the river zone before ultimately making their way to the ocean, where they then spend a few further years before ultimately returning as an adult. So these species really go through both salinity and temperature gradients as they travel to and from the ocean and river domains. So ultimately, given that, Atlantic salmon migrate to and from what we call these coastal rivers. So we have tributaries, which are located near the headwaters of the rivers, where salmon in particular like to spawn. And then as they travel to the ocean, they travel through these meanders along coastal rivers before passing through this estuary zone, before ultimately making it to the ocean. So when we think of ecosystems and specific organisms, and really they have multiple factors that can influence their survival and success in the water, but one of them in particular being water temperature. So water temperature closely is connected to many biological and chemical processes. It's also an indicator of how healthy a water body is. It can really be indicative and tell us what type of plants and animals can live within this water body, as well as in particular for salmon, it can affect various aspects, so such as the breathing. So when we have water temperature rises, this dissolved oxygen in the water decreases, making these warmer areas less habitable for Atlantic salmon. And then it can also impact their reproduction, feeding, and mortality of salmon. So as shown here on the right, at certain life stages, they have these specific ranges of water temperature where they're optimal in surviving, and then they have this optimal range based off of their physiology. So on this ocean side of coastal rivers, during the Atlantic salmon's life cycle, we can see that an increase recently in research on reporting ocean warming and marine heat waves. It's also predicted that into the future, there will be further ocean warming and longer, more frequent marine heat waves. So this has a direct impact on the health of ocean ecosystems, where certain increases in temperature could have lethal consequences for some organisms. So really, in addition to that research on ocean warming, there's new research coming out regarding the changing ocean currents by either slowing down, speeding up, or potentially shifting within the ocean, which can ultimately result in this redistribution of heat within the ocean. And so again, when we think of that, it could explain why, in some coastal areas, specifically in Atlantic Canada, we're now seeing some tropic aquatic species in our waters that weren't here many years ago. So really, in looking at that in the context of Atlantic salmon, while they're unique species and have a great ability to adapt to these changes in water temperature over time, this ocean warming will likely introduce new predators for the aquatic species. And then on the flip side, when we look at freshwater systems in rivers, we can see that it is heavily documented to show that there is some widespread river warming and thus this loss of cold water habitat for these aquatic species due to climate change. And so it's been increasingly common to have these local rivers closed to anglers due to these heat waves and increases in mortality rates of Atlantic salmon due to the thermal stress that they exhibit during these times. So as such, efforts have really shifted to conservation and restoration with the goal of protecting Atlantic salmon habitat. So one of which I just show an example here on the right, which is some of the work that the Nova Scotia Salmon Association, as well as others, did at the West River in Cheat Harbor, where they put deflectors along the river channel to aid in Atlantic salmon habitat. And then when we look at where those two domains converge, it's where it's located in estuaries, so really where these rivers meet the sea. So they're semi-enclosed coastal water bodies that have this free connection with the ocean. So really we have these nutrients brought in from the riverine setting that are then met with ocean nutrients, resulting in estuaries ultimately hosting the most unique ecosystems in the world. And it's also important to note that in estuaries we have this brackish water, where the salt water is diluted by fresh water. So this can change both in space and time, depending on the site, as well as due to the tidal cycling. So really, this zone is a unique place where Atlantic salmon can easily find food, as well as stay kind of sheltered before they ultimately make their way out to the ocean. And here, I just wanted to play a quick video of just a small school of the salmon kind of being forced out of this section due to the tide going out. So really, in estuaries, you have this unique habitat due to this tidal range that they experience. And here I just wanted to touch on that in estuaries, we normally divide it into 4 major zones. So we have the lower, middle, and upper estuary, as well as the river domain. So all of which vary in terms of this salinity gradient that the aquatic species feel, as well as the mixing dynamics vary within this zone. And then if we look at this conceptual model on the right, we can see that as freshwater feeds into an estuary, since freshwater is less dense than saltwater, it rises to the top of the water column. And with saltwater coming in due to tidal cycling and the tides coming in, we get what we call this saltwater wedge. And then, of course, due to tidal cycling and other effects such as rainfall events, we have this certain mixing capacity happening within estuaries. So depending on this connectivity to the ocean shown here, estuaries can be either tide or wave dominated, which vary throughout the day and from location to location. So at low tide shown here in these systems, in particular in the summer months, we can see cooler inputs, so such as this groundwater spring, as well as this cooler tributary. However, if we flip that at high tide, we can now see that at the surface, the groundwater springs aren't as detectable, as well as this cooler tributary extent is minimized. So really this is emphasizing the complexities of these systems, where if there are groundwater springs that provide thermal refuge for Atlantic salmon, the question becomes, is this consistently the same coverage over time, or does this really change with the tide? So jumping into some of my specific research and looking at the data that I collected over the past 2 summers, I have 4 study sites located in the Maritime, so 2 of which are in Nova Scotia. So we have the St. Mary's River here, as well as the Chéticamp River. And then in Prince Edward Island, I also have 2 sites, so that's the Morell River, as well as the Basin Head Lagoon. So they all have contrasting hydrology, geology, and hydrodynamics. And so my overall goal with this research is to conduct both thermal and salinity monitoring at these sites and investigate the thermally sensitive estuaries of these zones and their linked hydraulics. And with that, use that data to create a corresponding conceptual model. And once I have that, I really want to consider what these implications of climate change has on the ecosystem health within these zones. So for my monitoring methods, I conducted both spatial and temporal mapping of water temperatures, some of which using this hobo tidbit logger at the bottom, as well as LTC loggers, which measure level, temperature, and connectivity. And these were placed at discrete locations within the estuaries in this array configuration shown here, where we have this bottom logger that can be put in the PVC casing and top logger attached to this rope with a buoy at the top, just so it can move up and down with the tide. And so I also used, for spatial monitoring, my lab's drone that's equipped with thermal infrared imaging to detect really this surface water temperature at a spatial scale. And I also used this fiber optic distributed temperature sensing system to detect water temperature along a 1 kilometer stretch of fiber optic cable. So the first study site I'd like to talk a bit about today is the St. Mary's River. And it's one of Nova Scotia's longest rivers, and it's really famous for its population in Atlantic salmon. Given my data that I collected, it has a tidal range of approximately 2 meters. And it really has this deep outlet that functions as a harbor. So as the harbor is so long and has a large depth, we can see that as we move from the mouth towards the bridge temperature logger, which is shown in green here on the bottom plot, the temperature increases due to this cooler ocean temperature within the summer. And then again here, plotted at the top, we can see that there's little stratification occurring which I predict is due to the connectivity to the ocean, where we have this higher capacity of mixing due to these wide outlets. And just to note, this is the water temperature plotted for the month of August in 15-minute intervals for data collected that I collected in 2020. So with that data, we wanted to tease out a bit more of the forcing. So we conducted this frequency domain analysis by really converting this water temperature to specific signals. So shown as the amplitude in degrees Celsius on the y-axis, plotted against this frequency, so 1 over an hour on the x-axis. So we were able to detect dominant frequencies that correspond with specific periods, so that of which being this 12, 12.42, and 24-hour periods, which these correspond to semi-diurnal cycling as well as diurnal cycling. So for the diurnal cycling, it's primarily influenced by solar radiation, and with this semi-diurnal phases, we have that due to this tidal forcing. So at this harbor location here at the outlet, we can see that it has this strong tidal influence. However, as we move more upstream, for instance, to the new development area, as well as Cameron's Cove, we can see that there's this switch occurring where it's then dominated by solar radiation. So this is likely because the outlet is quite deep and wide, but as you move upstream, the river becomes more shallow, making it more susceptible to changes in solar radiation. So next, I'd like to talk about the Chéticamp River. It's located in Cape Breton Highlands National Park, and it's well known for this cold Atlantic salmon river. It has this shallow estuary located here, as well as this narrow outlet where it's quite protected from ocean effects. And the tidal range is approximately 1 meter. So again, just to play a quick video. So here we have that the tide is going out, and actually within this zone is quite a common area for a salmon pool for anglers to fish at. And it's being met with this ocean forcing. So we can see again that the estuary is quite protected from wave influence, meaning that it is dominated by tidal influences. So this map here shows the Chéticamp estuary as well as the logger locations, so 4 of which had both the top and bottom loggers within the water column. And then here again, I plotted the 15-minute interval water temperature data for the month of August in particular, just because this is where the thermal maxima occurred. So the top one here shows the center, stream, and spring logger. And I would just like to draw your attention to the spring, which is shown by the black line here. So during these high tide events, we can see that the groundwater spring goes from detecting the groundwater. As the tide moves up to high tide, it then matches similar water temperature levels within the main river. And then during this low tidal range, we can see that it consistently detects this groundwater temperature throughout it. And then the bottom 2 plots show the interior north and mouth loggers. So in these plots, again, we can see that the dark color shows the bottom logger locations, and the light shaded region shows the top logger locations. We can see that there's a lot more stratification occurring compared to the St. Mary's River. In particular, though, similar trend in that there is more stratification occurring as you move further away from the mouth. So a similar frequency domain analysis was conducted, and we're able to see that for locations with a top and bottom logger, the top water temperature is dominated by the solar radiation, whereas the bottom shows similar influences from solar radiation and tidal cycling. And here. So really moving away from Nova Scotia. So the Morell River is an Atlantic salmon river in Prince Edward Island that's located within the traditional fishing grounds of Abaquik First Nation and has a tidal range of approximately 1.2 meters. So in the map here, we can see that the Morell River feeds into this St. Peter's Harbor, which then feeds into the ocean. And again, there's little stratification occurring, but a bit more than the St. Mary's, as it's more protected from ocean forcing. And then the bottom plot here shows the trail conductivity data. So we can see that at the beginning of August, there's really this clear difference in both the top and bottom conductivity, signaling that there is a saltwater wedge at this location. However, as we move further to the second half of August, we can see that quite a bit of mixing occurs, which is likely due to, in the middle of August, there was a rainfall as well as high wind events that created the mixing to occur. For my last and final study site, it's in the Basin Head Lagoon located in Prince Edward Island, and it's a marine protected area due to the unique coastal environment containing the endemic giant Irish moss. It's also the shallow lagoon with really an abundance of groundwater springs. So I'd just like to show a few videos here. We can see that we have quite a bit of a high discharge rate from the groundwater coming into the main lagoon. As well as here, we can even see that at certain locations, the groundwater at low tide even bubbles up, where you can see it at the surface. So Jason, who I mentioned before in 2019, had really selected these monitoring locations shown in the map on the left here. So these include locations in tributary streams, as well as springs along the lagoon, as well as both he installed arrays for bottom and top water temperature locations at several locations within the lagoon. So on the right here, I show a few of these plots from the data that I collected from 2021. So as the lagoon is quite shallow, there's not a lot of thermal stratification in this upper arm region that you can see here. And for the groundwater springs shown in the middle section here, we can see again that at low tide, it really detects this groundwater spring, but as the tide increases to high tide, it again detects similar water temperature levels to that of the main lagoon, just a slight decrease though. And then here for spring 1, we're seeing this high water temperature range, but I guess don't fret, it's not the water temperature, it's just some of our locations over the summer. A few of our water temperatures became exposed to air temperature, so at these range, it's just detecting the air temperature. And then finally, the bottom plot here are just a few of the streams, so we can see that they're really groundwater fed, where the water temperature is quite lower compared to the main lagoon, which is great for fish, great thermal stress relief during high stress events. And then again, just this frequency domain to trying to see the dominant features of these estuary signals in water temperature. So here we're able to see that there's really this clear diurnal and semi-diurnal signals detected. And within this main lagoon, so this upper arm shown below, it shows quite dominant diurnal signals due to this solar radiation. However, if we look at these springs here, we show that there's strong influences by both the diurnal and semi-diurnal signals. Also, I would just like to kind of plug some of Jason's work because he has published a bit so far from his research from Basin Head Lagoon. So he really conducted drone flights several times throughout a tidal cycle to show how thermal plume dynamics change. So shown here in this quick video, we can see that at high tide, we can't really see a whole lot of the groundwater spring, but as the tide goes out to low tide, we can see that we're able to see more and more of the spring and ultimately have the flow direction change and follow that of the main channel flow. So that's really just emphasizing how the tidal current influences the plume morphology. So while thermal imagery can give us some great insight spatially on locations where there is cooler water. There is this limitation of that it only detects the surface water temperatures. And then again, when we look at these discrete locations of the arrays that measure both the top and bottom water temperature, they also can give us great insight. But again, the limitation is that you can only place however many loggers you have. If you had all of them, I guess you would cover the whole estuary, but there are limitations in that regard. So really tying in the whole picture of the thermal controls, you can really pair it with this DTS system and really spread out this fiber optic cable in such a fashion where you're able to tie in the other monitoring methods and gain a full picture of what's going on. So with that, this past summer, we had just got the DTS system in our lab, so we were able to head out into the field and conduct DTS monitoring with paired drone flights over a few days at both the Basin Head Lagoon as well as Chéticamp River. So some of which is just shown here as the Basin Head Lagoon. And even here, I was lucky enough that during data collection periods, there were heat warnings in effect, which kind of poor to conditions to work in, I guess, but it makes great data, especially when you're working with water temperature and groundwater springs. So here, I just wanted to show a quick preliminary plots of the data, as I'm still just working through analyzing them. But here on the bottom, we have the two satellite images that represent, this line here represents the configuration in which the DTS system was laid out with. So this zigzag section was fixed to stakes, which were then put into the stream bed, and the DTS is at the stream bed of the water column. And then if we look at this rectangle section, it's detecting water temperature attached to buoys. So it's wrapped around at the stream bed, as well as wrapped around at the top of the water column. So here we have paired thermal imagery from our drone. So we can see at high tide, while we're able just to detect the groundwater spring via thermal imagery, the DTS doesn't pick it up that great. We can see that it is cooler water temperatures compared to the main lagoon, which is great, as the Atlantic salmon would get some relief during those periods. But it's not picking it up like if you were to look at low tide, you're really seeing these clear groundwater temperatures around these 8-9 degrees coming into the picture, as well as that thermal imagery. Again, it's picking it up, and this is just because of the water column being so shallow compared to the high tide. So really just emphasizing the complexities of these intertidal groundwater springs experience during a full tidal cycle. So I'd just like to conclude with some final thoughts of the research that I've conducted thus far. So it's really clear that estuary thermal regimes are complex and are influenced by atmospheric, oceanic, and hydrologic thermal exchanges. And really this connectivity to the ocean impacts this thermal mixing, and thus predicting that some estuaries could be more susceptible to effects from climate change, such as an increase in really this storm surging, for instance, which would create this rapid thermal and salinity mixing. And then finally, the tidal cycle creates unique thermal plume dynamics within estuary zones. And then finally, just looking forward to some of my future work, I'm going to finish up processing the remaining of my 2021 data, as well as help that in aiding my conceptual model to finalize, and then use that model to then make specific management plan recommendations to certain species, so in particular the Atlantic salmon in this case. And finally, I just would love to kind of acknowledge the support from the local salmon watershed groups that really aided in giving me site-specific knowledge, as well as providing a lot of field support. So it's been greatly appreciated over the 2 years of the field-intensive campaigns that I've ran. And I guess with that, yeah, I'd just like to thank you all for attending my webinar today, kind of the first of such, and hopefully many more for me to go. So it was a pleasure, and yeah, I would open it up to any questions if anyone had any.
Thank you so much. That was an excellent presentation. We will now open it for questions and answers. Like I said at the beginning of this session, there's two ways of doing this. You can always type it in and I will read it out loud for Kathryn to answer. Or if you want to ask your own question, you can raise your hand and I will unmute you. So I'll wait to see if there's some questions coming in. I don't know if it's a question or not, but René Aucoin said from Chéticamp that he just managed to get in on the webinar, so. But he put in the question box. So I'm not sure if he had a question associated with that or not. He does have his hand raised, so just a second. René, go ahead.
Okay, and my apologies for being late. My internet reception here is not very good, and it took a little while to figure it out. Anyway, was there anything, and of course I'm referring to our own system, but it could apply to anyone. Was there anything particularly unusual that you found?
In the Chéticamp you're talking about?
Well, it could be other rivers as well, but I mean, that's the one that I'm looking at, but.
Yeah. Not really. So I will say I was able to detect an abundance of groundwater seeps in Basin Head Lagoon, as well as a few in Chéticamp, even within the Estuary Zone. So I could fire off those the data. I do have data for that for the springs, as well as thermal imagery. And really within Basin Head and Chéticamp in particular, as well as the Morell, I was able to see clear thermal stratification as well as salinity stratification. That's just from what I see is just because of the connectivity to the ocean, whereas the St. Mary's River, there was little to no thermal stratification occurring. But yeah, in terms of that, I'm still working through. I know I collected a section of the DTS cable there that Jillian and your crew helped me deploying, but I'm just working through getting and processing that data.
So just one more follow-up. So the stratification, cold water would have been on the bottom.
Yep, in terms of some periods with the tidal cycling, however, you do get kind of this switch of the thermal stratification occurring, so where you would get the opposite, but in majority of the cases you get thermal stratification occurring where you have the cooler water temperatures located at the bottom of the water column.
Yeah, it's pretty evident over there, just swimming there.
Yeah.
Notice I've been swimming there since I was a kid, and if you follow, really go down low into some of the channels, you hit some really cold water most of the time as compared to the upper water level.
Yeah, you've got a nice river in the sense that it's still quite cool compared to the other systems, I'd say, Renee.
Lots of water here. We've had 2 phenomenal rains the last couple of weeks. In fact, everyone's heard about the one 2 weeks ago. Mm-hmm. And so that would have brought and these are just side facts, maybe of interest, but would have brought the water level upriver around the campground and that about 5 feet 2 weeks ago. And believe it or not, yesterday, water came up an extra, I would say an extra foot. So 2 weeks ago with that big rain, although we were off on the side a little bit, so we didn't get as much. The water went from 1 meter to 2.5 meter. And yesterday it went from one meter thereabouts or a little bit more to 2.7. So we had a huge rainfall up the mountain yesterday. Sign of the times.
Yeah, honestly, I know. And I pulled my loggers before that happened, which was unfortunate. We were kind of bummed about that, but I was able to get the one of the hurricanes that happened in 2020 which showed level increasing significantly in the Chéticamp estuary, as well as basically all of the water temperature reached the exact same, as well as the salinities, just due to that mixing from the rainfall event.
Merci, René. Kathryn, there's another question. I'm going to read it out loud from Sarah Whitley. It's how frequently would one need to fly the drone with thermal imagery in order to get a general idea of the thermal regime in another river system? And how long does it take to cover an estuary?
Yeah, for sure. So depending on the size of the estuary, so we have the DJI Matrix 210 RTK drone. So you have two large drone batteries that you put in the back, and they last, if you're doing specifically orthomosaic, so stitching, which I've shown in a few images, they last about just under 20 minutes per battery set. But if you were just like investigating to see if you have any thermal anomalies, you could stretch that out to like 25 or plus per battery, and it takes a lot faster in terms of getting your spatial coverage in that regard. And in terms of when to fly the drones, so if your whole purpose is to look to see if you have any cooler inputs or thermal anomalies occurring, you would want to fly it at the maximum of the day. So around noon time or just after, where you're getting that high contrast and it can really pick up within the thermal imagery.
Thank you. And I think as of right now, that's our questions. I'm sure some will have more once they start thinking about it. So if you do, please feel free to ask your questions by sending us an email, and I'll make sure I share it with Kathryn and get back to you with an answer. Kathryn, thank you so much for a great presentation. For anybody that was not able to attend today, as you know, we record these sessions and we do post it on our YouTube page. So it's always available there. So please share with your friends. And I also wanted to remind the group that we will have more webinar series coming up. If you look at our website under webinar, you'll see a list of those. Our next one will be from Thomas Buffin-Bélanger from UQAR, and his presentation for the next one will be in French, and it will be on hydromorphological sensitivity of salmon rivers in the Gaspé and Lower St. Lawrence. So once again, I just want to say a big thank you to Kathryn and everybody else that participated today, and I hope we do see you real soon. So thank you.